methods of quality control. So let's start with a simple example, right? Let's think about we are interested in manufacturing a car, right? And then we want to make a car that meets the desired quality levels, whatever quality. Think of quality in the terms that you're thinking, okay? Or think about, so in this case, actually, let's come to this example. Or you know what? Let's actually take this example. Think about, you know, we want to manufacture the hip implants, and we want to use an additive manufacturing process to manufacture these hip implants. And then when you think about the process here is the additive manufacturing process, right? And your controllable factors in this case could be the material that you are interested in, the process temperature. So if you think about additive manufacturing essentially melts down the powder particles and then deposits them layer by layer. So the temperature at which it melts the powder particles is crucial and controls the overall quality of the manufactured part. So you can think about the process temperature. The curing temperature is kind of like a post-processing step when you reheat the part. So some of the defects can be removed from the manufactured part. Laser power, it's the laser that actually melts the metal powders. So you can think about multiple controllable factors in this case. All right, so the first idea of quality control or the one approach to controlling the quality is design of experiments, right? You may or may not have taken a design of experiment course already, but I'll try to give you a brief understanding of what design of experiments is. Think about manufacturing this hip implant, or think about manufacturing anything. When you think about manufacturing something, you think about the optimal process condition required to manufacture something, right? For instance, if you are planning to manufacture a car, you would not want to use iron for the chassis because iron is too heavy, and then your car would be too heavy to drive, very less fuel efficient. Think about the hip implant. Hip implant, you don't want to make the implant out of copper, because if you make it out of copper, it's going to be very soft and it would, you know, break very easily. So you want to make it with something, a metal that is very strong and does not react with the internal organs or the, you know, the blood and the internal muscles. So design of experiments basically says that you have a bunch of controllable factors, and then think about a knob. You can turn the knob and set each of these process parameters at some specific values, right? And it tells you it basically gives you the methods and the principles and the concepts by which you can identify the combination of process parameters that leads to the highest quality levels, right? So let me try to write down this definition. Basically, it tells us methods to identify the process parameters. When I say process parameters, think about controllable factors, right? Identify the process parameters, or I should say identify the levels. Levels means values of process parameters that leads to the highest quality, right? In some ways, we basically want to optimize the quality of the part, right, by doing so. All right, now how do we do this? We basically do something called a factorial design, in simplest way. What you would do is, let's say if you have 10 different parameters to control, you would fix all the parameters at certain values, and then you would just change one of the parameters. And then you see how does the change in one of the parameters changes the overall quality, right? And then you do this for every single parameter. Now, design of experiments give you some more intelligent ways of doing this. And again, we're not going to go into the depths of that, but the idea is to conduct experiments, conduct simulations or experiments with different combinations of input parameters to identify the optimal process conditions, or to identify the process conditions that leads to the optimal quality levels. Does that make sense? All right. So again, DOE is not the focus of this course. There is a whole course, an entire course that is there on design of experiments. And if you're interested, I would strongly encourage you to take a look at that course. All right, now coming to statistical process control, which is what this course is about. Statistical process control is basically saying that once you have a process set up, running, and measuring the quality levels, the idea of statistical process control is to measure not measure, but in some ways monitor the quality levels, identify if there are some anomalies in the process, and then take corrective actions. So if I have to define statistical process control, I would say it's about monitoring it's about monitoring the quality level of a process, identify anomalies, and take corrective actions, right? And then typically the process for doing a statistical process control is by using something called a control chart, right? And then we'll spend a lot of time throughout this course talking about control chart, how to construct them, and a lot of time on how to use the control charts. This is a very general depiction of what a control chart usually looks like. You have upper control limits, which are called UCL. So you have upper control limits, and then you have lower control limits. And then you'd want to monitor if your process stays within the control limits or not. If it is outside the control limits, you can say that that measurement or a specific measurement is outside the control limits. And then the last method is acceptance sampling. The idea of acceptance sampling is that in many cases, I wouldn't say necessarily hip implant, I would say something like when you are manufacturing bolts. So something which is simple and not very complex. So what you do in the acceptance sampling is basically you are manufacturing thousands and thousands of these bolts, and you can't really inspect every single bolt. So what you do is you take a small sample from that big lot of thousands of bolts, and then you just assess the quality of this small sample, right? So let's say out of these 10,000 bolts, I would sample 100 bolts, and then if 95 of these 100 bolts meet the quality levels, then we accept the entire lot. Otherwise, we reject the entire lot. Right? So you can see we are basically using a sample to make inference about a big population. Right? So usually it's a good idea to use such a method, but in many cases, if you think that there's a lot of variability in the process, then such a method of acceptance sampling may not be the best. But again, it's useful if the parts are not very critical or complex. All right, so again, to summarize, design of experiments is a method that allows you to identify the combination of process parameters that leads to the highest quality level. Once you have set up the process, this is where statistical process control comes into picture. And statistical process control is about monitoring the quality levels to identify anomalies, potential anomalies, and then you can take corrective actions. And acceptance sampling is basically you take a small sample out of a big lot, and then if this small sample meets the quality levels, then you accept the entire lot or you reject the entire lot. Right? So take a look at an example here. Let's see, a lithium-ion battery manufacturer wants to optimize the life cycle of lithium batteries. Okay. The manufacturer records the time to discharge of lithium-ion batteries produced by different combinations of process parameters, right? So this manufacturer is basically running experiments with different combinations of process parameters, and then they are recording the time to discharge. So you can think of the time to discharge basically a quality characteristic, right? I can measure the time to discharge. For each combination, the manufacturer records the time to discharge of 100 lithium-ion batteries. So we're doing this experiment on a total of 100 lithium-ion batteries. Okay. Right, determine which combination of, so now we have scenarios on the left-hand side, and we have to match these scenarios with appropriate methods. So if we think about determining which combination of process parameters led to the longest discharge time, then if you think about this, this is basically design of experiments, right? And then the second question is determine which batteries are defective. This is what you would do typically using statistical sampling, statistical process control. You can also think about this as acceptance sampling, but in acceptance sampling, we are not very much interested about every single battery. We are more interested in a whole sample, right? But if you want, you can also think about this in terms of acceptance sampling. All right, so now, so far, we have studied what is quality control. Quality control means reducing variability. Improving quality control means reducing variability. We have studied different methods of doing quality control. And now let's talk about when to use each of these different methods of quality control, right? So you have design of experiment, you have statistical process control, you have acceptance sampling. Now, typically, when you have, let's say you go and join Intel tomorrow, right? Or any other firm, as a matter of fact, and let's say you are the quality engineer. Once you start investigating the process, at this time, if you're not aware about any specific quality control issues, then you'd want to start with something which is very, very simple. The simplest one here is acceptance sampling, right? So as if you think about the time that progresses, as time progresses, you want to start with acceptance sampling. Over time, let's say you start observing some consumer complaints or some defectives or some breakdowns in the process. This is where you want to slowly turn to process control. You want to start monitoring over time how your process is performing, right? And let's say at some point in time, you figure out that there are some serious concerns with the process. And so this is where you would want to go and invest in design of experiments. So you can use design of experiment methods to, in some ways, redesign the process. Redesign the process. Think about design of experiments. It's kind of like you're changing something at a very large scale, right? You're changing the process setting, you're changing the materials, or you're changing the raw materials, you're changing the supplier, and you're changing so many things. So design of experiments is something that you'd want to do at the last stage while you are doing process control, right? So towards the end of this life cycle, you want to spend equal amounts of effort on process control and design of experiments. And by looking at this chart, it might also have been a little bit apparent to you that if you're doing acceptance sampling, it would not have significant impacts on quality, right? Whereas if you do design of experiments, you would have huge impacts in quality, right? So this will lead to maximum increase in quality. And then acceptance sampling will lead to lowest improvement or increase in quality. Let me correct this. All right. And so if acceptance sampling leads to lowest improvement in quality, that means it also leads to lowest reduction in variability, right? I can say that this leads to lowest reduction in variability. Right? And then design of experiments leads to highest or maximum reduction in variability. Right? Okay, so just to close this chapter, a couple of more things, just to bring everything back into perspective. In statistical process control, you would typically start with certain input factors. Whenever you think about the process, think about the inputs to the process, to your process. Right? You have certain controllable factors, you have certain uncontrollable factors. You measure the quality, you collect some data, do data analysis. This is where we do control charts, evaluation. Then you would do diagnosis. This is where you would identify if there are some breakdowns in the system or anomalies in the process. You identify those anomalies, and then you formulate an action plan to take some corrective actions. And then you come back to these controllable factors, adjust these controllable factors, and then you continue monitoring the process. Right? That's in a nutshell what statistical process control is. Right? And then the last topic, which I'm not going to spend too much time, is Six Sigma. Six Sigma is very closely related to quality control. If you think about Six Sigma, and if you have taken any course on Six Sigma or not, Six Sigma usually involves 5 important steps: define, measure, analyze, improve, and then the last one is control. Right? So control is what really quality control is about. So Six Sigma is very, very closely tied with quality control. And again, I'm not going into Six Sigma again in this course. You have an entire course on Six Sigma that you can potentially take. Right, so I'll stop here for this lecture. As I said earlier, I would upload all the lecture notes that I'm making right now into a PDF file, and then I will make the video and the lecture notes available just after this lecture is done. All right. If you have any questions, feel free to send me an email, and thank you.